Okay, so yeah, I guess the screen is visible, right? Hello?
Yes, ma'am.
Yeah. Okay, so yeah, so thanks to all of you for coming here for the afternoon class. So we were talking of constraint optimization, and yeah, so one thing before I start off, I just want to mention that regarding references, there's one reference I gave you on this textbook by Nosidal and Wright. So I'll probably update it with some more references. But word of caution regarding all these textbooks, sometimes it might not be consistent with the lectures, I mean, in terms of the notations and things. And also, what I've seen is these textbooks, it's not very easy to parse through them. It's the first time that most of you are being exposed to this topic. So it's not very easy to, go through the details because a lot of small details, and it's a truly rigorous treatment that all these textbooks give. And some of these points are like, very fine points, and they are meant to, deal with scenarios where, even every scenario. Okay, so even there's some corner cases that arise, and it's presented in a way so that even those are dealt with. Okay, so since it's a first course, and I think it's already a lot of information, so I wouldn't want to go into those details. I'll just, tell you as and when such details I'm going to talk of. Okay, but we're not going to prove some of those things. But some of these textbooks justify all these optimality conditions in a very rigorous way, covering every possible corner case. Okay, so that's just something to keep in mind. So what I would suggest is understand the class fully, the lectures, the current lectures that are going on. It's important that you understand those fully, and if you have any questions, let me know. And once this is clear, it's fine to go and check out other references. Okay. So yeah, so that's just the thing. And okay, so let's just begin. So yesterday, what we were doing is I introduced you to the constraint optimization framework, and we started off with the case where there's one equality constraint. Okay, so the problem was of this form: minimize f of x such that h1 of x is 0. Okay, so the example we took was something of that form. Okay, so this was x1 plus x2 such that x1 square plus x2 square minus 2 is 0. So it's basically the periphery of the circle, that is the feasible region. And, x1 plus x2, that's a linear objective. So, so overall, this problem is a nonlinear problem. Okay, and I showed you how like the same method that you used to geometrically solve linear programs, the same approach can be used here, where you sketch the feasible region and then you see the contours of the objective function and you see the general direction in which the function decreases and how far can you go. So that's one way to solve it geometrically. And then we were just trying to analyze what happens at the optimum point. Okay, so let me just do one small recap for the case where for a general function h. Okay, so suppose so we are trying to see that given some point is optimum, what can you say about things like the gradient of f and the gradient of h, okay, of h1. So suppose a function was something, the h, so this is the curve h1 of x is equal to 0. Okay, and suppose we're taking some point here and we're trying to check if that's an optimum point. Okay, and the gradient of h, of the constraint at this point, from your earlier days, like when we had these exercises where you had to plot the contours and check the gradient. Okay, so so it turns out that this the gradient of h is going to be always orthogonal to the contour. Okay, so this is going to be gradient of h, gradient of h1. Okay, and now suppose the gradient of f is something like this. Okay, and the feasible region is exactly on this curve. These other regions inside, I mean, within h1, those are not included. It's entirely on this curve. That's the feasible region. And x is a point. So for this particular x, you have that it satisfies h1 of x is 0. So let me just call it x star, okay? So we have that h1 of x star is 0. Okay, and now you're trying to verify if there are, any other directions that you can go such that the function improves as well as you remain feasible. Okay, so we know that for some direction to be a descent direction, so the function value has to reduce. Okay, so then the condition for descent is what? So D is a descent direction if you have this condition, right? So D transpose grad f at this point x star is less than 0. Okay, so that will give you, so basically this hyperplane that I'm drawing here, this is everything that's orthogonal to gradient of f. So all vectors which make an obtuse angle with gradient f. So basically everything here. So let me just draw it in a different shade so that it doesn't cause confusion. So, these are all the descent directions, okay, all possible descent directions. Everything in this part of the half space, in this side, okay, but it shouldn't be on this line, on this perpendicular line to the grad f, okay. So something here that is not a descent direction, okay. So it has, because it has to be strictly less than 0. Okay, so that is the set of descent directions. Now, in terms of feasible directions, since you have to remain on this h1x, the feasible direction is something which is exactly orthogonal to gradient of h, because you want to remain on this curve. So it will be something like this, either this direction or this direction. Okay, so that it remains on the curve. Okay, so this would have, so you see that, when immediately, there cannot be a direction which is both feasible as well as a descent. Because if it had to be a descent, it had to lie on this side of this half space. And if it had to be feasible, it had to lie exactly on this hyperplane, where you cannot have some case like that. Okay, so if these two are in the same direction. Okay, so now in particular, what we are taking here is grad f of x star is it's in a direction that is it's not in the same direction as gradient of h. It's parallel, of course, but it's in another. It's pointing in the other direction. Okay, so this is one condition that we had. Now another case could appear. So let me just go down. So another case is, suppose you had a scenario like this. Let me just again draw it this way. So the gradient of h is like this. So gradient h1 of x star is like this. And the gradient of f also is in the same direction. Okay, they're parallel and they're also pointing in the same direction. So in this case, if you look at all the descent directions, so that would be, so this is the line orthogonal to gradient of f. So this is gradient of f, okay? And everything which counts as a descent direction would be in this space, okay? So everything which makes an obtuse angle. Now, in terms of feasible directions, again, it's everything on this plane, okay? So even in this case, you cannot, if somebody told you that x star is an optimum, is a minimizer, then there's you would believe it, okay, because there's no descent direction. So this is a case where delta fx star is in the same direction as gradient h of x star. So in particular here it's lambda greater than 0, here lambda greater than 0. So both these conditions are fine, okay, both these conditions could occur if x star was an optimum. But whereas, let's just take the other case, so when neither of these happens. Okay, so something like so h grad h is like this, and now let's say grad f is something like this. Okay, this is grad f. Okay. So again, now if you look at all possible descent directions, so this is the line orthogonal to grad f. So basically everything, all directions in this half space, those would be descent directions. Now in terms of grad h, okay, in terms of feasible directions, everything these two, right? I mean, which is along this line. So these two are feasible. Okay. So now in particular, if you take this particular direction, so the one that I've drawn to the, pointing downwards. So this one is feasible. It's as well, it's a descent direction. Okay. So here we know that X star cannot be an optimum in this case. Okay. So in general, the condition is that, grad fx star is equal to some, let me call it mu, okay? Some mu times grad h1 of x star, where mu doesn't have any sign restrictions. Okay, so this is what we saw through an example yesterday. So I'll just do a formal proof of it. So in particular, we are looking at x1 star, x star, and we know that h1 x star is equal to 0. It's a feasible point. And we are trying to look at a direction d, so that the new point becomes x star plus d, and that also lies on the curve. So h1 of x star plus d is also 0. Okay, so now by applying the first order Taylor series approximation, this is what you will get. Apply it around x star. Okay, so all this is x star. Okay, so now this is the first order Taylor series approximation, and this is equal to 0. Okay, and you want this also to be equal to 0. So it should be that d transpose gradient of h1 of x star should be equal to 0. Okay, so this is what we were seeing here, right? I mean, we saw the directions orthogonal to grade of h, gradient of h. Okay, so this is the condition you need for feasibility. And now in terms of descent direction, we already saw from our concepts in unconstrained optimization that you need this condition to be true. So in short, you need a direction d. So, so the idea is to check if there's a direction d. So all this is for x star, okay? So is there a direction d such that d transpose gradient of h1 x star is 0? And d transpose grad f of x star is less than 0. Okay, so is this condition clear? Are you all with me? Guys, yes, no? Yes? Okay, yes, okay, good. So, yes, fine. So yeah, thanks for the response. So this is what you want to check. When if somebody tells you that x star is the optimum point, you check whether this system is feasible. So is there a d which satisfies this? Okay. So now if x star is an optimum, if x star is optimum, then it implies that you cannot have such d's. So it means that this system, this system is infeasible. If x star is optimum, then it should be that this system here, this one, is infeasible. Okay, so there shouldn't be any such d such that this holds. Now, this is where the Fatka's lemma kind of things help in this aspect. So you saw one problem that we had in the midterm, right? So it was in particular this example. So the second question here in the midterm. So it said that exactly one of the two systems is feasible, and I think by now, if you've gone through the solutions, you would get a proof for this. It's just by elementary algebra, or you could prove it using Fatka's lemma. Okay, so so let me just say, I mean, I've just written it here for convenience. So only one of the two systems is feasible. So D such that D transpose A equals 0, D transpose B less than 0. This is one system, and the other where B can be written as mu times A for some mu in R. So mu doesn't have any sign restrictions. Okay. So now if you apply this to the system here, so only one of the two systems is feasible. So you could set A. So the particular substitution would be A is grad H1. Okay. And B is grad f of x star. Okay, so if you do this, so this system is infeasible. So it must be that this corresponding system is feasible. So what that means is gradient of fx star can be written as mu times gradient of hx star. So gradient of the function, the objective function, is mu times the the gradient of h, okay, at x star, and for there is some mu. So the meaning of this is, since if x star is optimum, then this you should be able to find some mu such that this equation is satisfied. Okay, so this is an optimality condition. So this is a test for optimality that you can do. Okay, so it's necessary. So if x star is optimum, this has to be true. Okay, we're not saying that, if this happens, whether x star is optimum, no, that's still not what we are saying. It's a necessary condition. Okay, so I'll just pause here. Is this clear? Are there any questions? So some of you were asking me about Fatka's lemma, right? Like where the application comes. So it's in all these concepts, like deriving these conditions, Fatka's lemma is useful. Okay, so is this clear? Any questions on this? All of you with me? Yes, no? I need some response. Yes? Okay. Good. Okay, so this is the case for one constraint. Now, suppose you had more than one constraint, right? So suppose you had several such constraints. So there are L of them, L equality constraints. So how would you write it, right? What would you can extend the same idea there. So can you tell me what the conditions would be? So remember we wanted, x star was the point that was given as optimum. Okay, so it was feasible and it's optimum. So all these are satisfied with equality. So, so in terms of, you wanted to check for a descent direction. So what is the condition? Can you tell me? So if you're checking if D is a direction you can move, D is a direction in which you can move. So it's a descent direction. So then what is the condition? Guys?
D transpose KLH 1 x star is equal to 0 and similarly for all h's.
Yes, so D transpose grad f of x star is less than 0. And also you want to maintain feasibility, you want D transpose delta hi of x star equal to 0. And this is true for all the I. Okay. So again, so now this would be, this here you have a system, right? So this is of the form. So let me just write it in a slightly different way. Maybe it's just easier to see it as grad h transpose D. So if it just helps with that way. So grad hi transpose D is equal to 0 and grad f transpose D is less than 0. Okay, so now you want to see if this system is feasible. So if x star is optimum, this system will not be feasible. So there is an alternate system again which is feasible. Okay, so for that you can use again the system that we saw in the same midterm exam, but the first part. Okay, or is it that first part? So it's equal to. So just hold on for a minute. X and bx less than 0. Okay. And yeah. So, okay. So you have to just extend this in a slightly different way. So in particular, if you have, the system, right? So let me say this is the A. So so this is like A transpose D is 0. Okay, so this I'm writing this A transpose D is equal to 0. And this is a system where B transpose D is less than 0. Okay, so there's a slight difference from this condition in the sense that, you don't have the D has to be greater than or equal to 0. So that difference is there. So let's just see how we can, fit it here, okay, to ensure that this is true. So, okay, so is this clear what I'm saying? Like we have to apply some notion of Fatka's lemma here, but we don't have it exactly in the form that we saw. Okay, so one thing is, I guess probably the one we did in class itself is in this format, right? So the system where you had one system was AX equal to B, X greater than or equal to 0. And the other was A transpose Y. Oh, you had less than or equal to. Okay, fine. So that is not the same thing. Okay. So, yeah. Okay. Yeah, so let's just see. So this is the system we had in the midterm exam was, let me just write that. So one was AX less than or equal to B, and two was A transpose Y equal to 0 and B transpose Y less than 0 and Y greater than or equal to 0. Right? Okay, so what you can do is you can just do this trick, right? So you can write a D as D plus minus D minus. Okay, so that will take care of this Y greater than or equal to 0 part. Okay, so let's just see that. Okay, so maybe let's just try to work with this example. Suppose you didn't have Y greater than or equal to 0. Okay, so let's just try to derive the condition here. So suppose, so this we know is true. This is one of these two is feasible. Only one of these two systems is feasible. Okay. So now we want to extend it to the case where one system is A transpose Y equal to 0 and B transpose Y is less than 0. This is one system, right? So you can write Y as Y plus minus Y minus. Okay, so A transpose Y is just A transpose Y plus minus Y minus is 0. And B transpose Y plus minus Y minus is less than 0. And Y plus is greater than or equal to 0. Y minus is greater than 0. Okay, this is, if you remember, this is one way in which we, we did a transformation to include these as, greater than or equal to 0, those kind of variables. Okay, so now this is in the form that we know. Okay, so so in particular, you have these variables Y plus and Y minus are the variables. So let's write a new A tilde here. So this is A. So let me just write A tilde is A transpose and also minus A transpose, right? Okay, and right, and B tilde, I'll just call it B. So B tilde transpose is B transpose and minus B transpose. Okay, so the claim is there is a system such that AX is less than or equal to B. So A tilde X less than or equal to B is true. Okay, so because this system doesn't have a solution. So then this would boil down to A, and this would be minus A times X is less than or equal to B and minus B. Okay, so what this means is AX is less than or equal to B and minus AX is again less than or equal to minus B. So this would mean that AX equal to B is feasible. Okay, so I just try to derive the Fatka's lemma version here. Okay, so what it means is that this system, if it is, so coming back to the optimum point, so this is an infeasible system and this is of the form A transpose Y equal to 0, B transpose Y less than 0, and you want that to be infeasible. So then it means that AX equal to B is feasible. Okay, so that would mean that, let's just write that in maybe in a new page. Or I'll just write it here itself. You can maybe see the steps later. Okay, so here the A. So can you tell me what the A is here? What the A boils down to from this system? Okay, are you all here? Okay. Can somebody tell me what the A is going to be? I've just written this as A transpose D is 0. So I want someone to tell me the A. Okay. I'm not moving ahead till someone speaks up. So there some confusion here. Okay, I think I'll ask somebody. Maybe Rajneesh?
Yes, ma'am.
Yeah, so is it clear what's going on? Can you tell me what is the A here?
Yes, ma'am. Grade h1 x star, grade h2 x star, then grade h
Yeah.
t or
Exactly.
something in that text.
Right, so all these columns are written as grade H, grade 1, grade H1, like that up to grade HL of H star, as many as the number of equality constraints that you had. And B is exactly grad Fx star. Okay, so now the condition is that Ax equals B is feasible. So what it means is that you can find a mu, so some mu like this, such that A mu equals B. This system mu is such that A mu is equal to B. This is feasible. Okay, so there's no sign restriction on mu. So what this means? So this means gradient of Fx star can be written as summation mu I gradient of Hi. Okay. Okay, so I can write it this way. Now, since there are no sign restrictions on mu, I can also just write it as gradient Fx star plus summation mu I gradient of Hi x star is equal to 0. Okay, so because there are no sign restrictions on mu, so there's a reason why I'm writing it in this form, because I will later generalize this into other cases. So this is the condition that an optimum x star has to satisfy. Okay, so I hope this idea is clear. It's just a generalization of the one constraint case. Okay, so now let's just maybe move on to the case of inequality constraints. So I take it that it's clear to you all. I'm not hearing from people, so I don't know what's going on. So please ask if there is some issue, if something is unclear. Okay, and particularly Fatka's lemma. I think Bhavna, you had a question, right? Like, where is Fatka's lemma used? So I think Bhavna, Yashi, you guys were asking, and I'm sure this is a question that many of you would have had. Okay, so these are the in the theory of constraint optimization, Fatka's lemma plays a huge role. Okay, so yeah, so this is about equality constraints. So now let's look at the case where you have inequality constraints. Okay, and yesterday we looked at this notion of active constraints. Okay, so that is something which will play a role here. Okay, so let's just look at this example where you're trying to minimize x1 plus x2 subject to x1 square plus x2 square less than or equal to 2. So in the example you saw yesterday, it was x1 square plus x2 square equal to 2, which was on the surface. But here you're looking at the region which is enclosed by the circle. Okay, and this is of this form g1x less than or equal to 0. So I'm going to look at whenever I write inequality constraints, I'm going to assume that it's going to be written in this form, gix less than or equal to 0. Okay, so here you have that gradient of f is 1, 1. And the gradient of g is also 2x1, 2x2. It's the same as what we saw yesterday because the left-hand side of the constraint was the same. Okay, so now let us take, so here again the optimum point is here. Okay, so by the same reasoning, so you look at x1 plus x2 equal to 0. I mean, these are the contours that you can look at. And how far can you push? So that is till here. So this is x1 plus x2 is 0. And as you go along this direction, so because the gradient of f is along this direction, the function is going to increase. And along this direction, the function decreases. And the best you can hit is somewhere here, okay, at this point. So it will be on the periphery of the circle. Okay, so in particular, this point, the point here is -1, -1. So that is the optimum point. Okay, so let's see what happens again. So we've already seen some part of it yesterday. So here the constraint was something like this, right? The gradient f was 1, 1, and gradient g was in this way. So this was -2, -2. So this was gradient g here is -2, -2, and gradient f is 1, 1. Okay. So here, one important thing to note is that even this entire region inside, this is also feasible. Okay. So if you're at this point, it's not only these orthogonal directions to gradient of g that you can go in, but you can also take any of these directions, okay, for feasibility. Okay. Now, whereas for descent direction for in terms of the function, the objective function, you need all these directions. Okay. So again, this is not possible here. So this is -1, -1 can be an optimum point. Okay. So one difference here is now suppose in general you had something like this case where gradient of g is in this direction and also gradient of f is in this direction. Okay, so suppose this happened in terms of the optimum directions for the objective function, you have all these are possible, all these are descent directions. Okay, now so the feasible region is everything here in this space. So all these directions that I've shown in blue are possible descent directions. Now, in terms of feasibility, these directions which are going in this, orthogonal to gradient of g, those are feasible. But additionally, these are also feasible. Okay, so that's why, if these are in the same, if these are parallel, but pointing in the same direction, this case, x star cannot be an optimum. So it's really important here that they point in opposite directions. Whereas for equality, the equality constraint case, it was okay if gradient of f was in either direction. It didn't have to be pointing in the same, opposite directions. Even this kind of a case, you couldn't find both feasible and descent directions. Okay, so formally speaking, in terms of the Taylor series approximations here, what you have is we are looking at a place where the constraint is active. Okay, so in that case, what you have is g1 of x. So this is the first order Taylor series approximation. So g1 of x is 0. Okay, and you want g1 of x plus d to be less than or equal to 0. So that the new point x plus d is feasible. So what you want is, this means that gradient of g1 of x transpose d should be less than or equal to 0. Okay, so that's the case we saw here. Okay, so in this case actually, so you wanted gradient of g1 of x. The d makes an obtuse angle with gradient of g1, and it also makes an obtuse angle with gradient of f, because for descent directions. Okay, so now one thing to note is if x is an interior point, suppose you took some point in this space. Okay, so now we already saw yesterday that it's as if the constraints don't matter. You can go in any direction, but still, you can stay feasible, right? So you just need to look at the descent, only the descent part. Okay, so in that case, the constraints just become like as in the unconstrained case, that gradient of fx equals 0. So if x is an optimum point and it lies in the interior, then the condition is just gradient of fx equals 0. So this also you can see, I think I'll leave this as an exercise to you because you're all very silent. So just try this out as an exercise. It's not too hard to prove this. Okay. So it again comes from these Taylor series approximations. Okay. So So in terms of the descent directions, in the case like equality constraints, let's try to use the same method here. So what we are trying to say is that this system, gradient of g1x transpose d less than or equal to 0, and gradient of fx transpose d less than 0. So this system has to be infeasible. Okay, if x is an optimum point and if x lies on the boundary. Okay, so then again we can use Fatka's lemma. So this is the version that we have seen in class. So in class, you remember we saw this, right? Either B lies in the cone of the vectors in A, okay, in the positive cone. So Ax equals B, x greater than or equal to 0. Or there is something which separates the two. So you saw something like this. You know, if A1, A2, and all these are the vectors, so maybe A, so this is AM, let me just call it AM. And so X lies somewhere here. Sorry, this is B, right? So B lies in the cone of them. So this is the first set of equations. So either B lies here, or if B doesn't lie here, then there is something which separates the two. Okay, so that is represented by Y. Y is the normal vector and specific. Okay, so I hope you remember this. So you can just apply this to this situation that we have in constraint optimization. So in particular, this system is equivalent to this form. Okay, so it's as if the d's take the values of the y's, and a, so a is just gradient of g1, okay, and b is gradient of f of x. Okay, so now since you want this system to be infeasible, so it must be that this system ax equals b, x greater than or equal to 0, that is feasible. So what it means is there is some, something like, let me just write it. So b equals ax, so gradient of fx is equal to lambda times gradient of g1x. Okay, so you want this to be true. So I think, okay, there's some mistake here. Can somebody tell me?
On the inequalities and not directly.
Yeah, so here, right? So I think 1 is greater than or equal to 0 and 1 is less than 0, right? So here my A is actually minus gradient of G1, okay? And here you'll have delta fx is lambda times minus gradient of G1, okay? Is this clear? Guys? No response? Yes. Okay, so in addition, you also want x to be greater than or equal to 0. So that would boil down to lambda taking a value greater than or equal to 0. So the overall system here becomes gradient of fx plus lambda times gradient of g1x is equal to 0, and lambda is greater than or equal to 0. So you need to be able to find a lambda such that this is true. So if x, so let me just tell you again. So if x is an optimum point, then it means that you can find a lambda such that this system is satisfied. Okay. So again, this will extend to the case of multiple inequality constraints. So in particular, one thing to remember is this is true if x is active at G1. Okay. So this holds only if x is active at G1. Okay. So if it's an interior point, if g1x is less than 0, then you won't have this kind of a thing. It just becomes delta fx is equal to 0. Okay, so this won't come in and it will just be delta fx equal to 0. So what you can also additionally say is that instead of saying x is active at g1, you can say lambda times g1x equals 0. Okay, so which means if g1x is strictly less than 0, then you don't care about that. So lambda is 0, so it will just become delta fx is 0. Now if g1x is equal to 0, then it should satisfy this. Okay. So in terms of multiple inequality constraints, it's going to be the same thing. It's just that instead of one column here, you will have multiple columns. So A is just going to be minus g1x minus g2x, like that. up to minus gmx. Okay, and d is again the same delta fx. Okay, so I hope this is clear. So you're going to just apply the same condition. So gradient of g1x transpose d should be less than or equal to 0 for all the active constraints. So this is the case for, so let me just say, like, suppose there are, suppose so first j constraint. So g1 of x equals 0. So it's an optimum point. X star is optimum. And suppose g1 x star is 0, g2 x star is 0, and so on up to some gj. Okay, not all of them. Some of them will be inactive. So let me consider only j of them as active. So here what's going to happen is you will only take those the ones corresponding to the active constraints. So g1, also only these ones for which g1 x star is 0. So you'll only take those. Okay, because remember it's only for those that we have that the gradient of gx transpose d is less than 0. So this is true only if x if g1 of x is 0. Okay, so this is what you'll get. And so what's going to happen is you will have a lambda 1 corresponding lambda 1 lambda 2 like that up to lambda j corresponding to each column of a. So what you'll have is summation, so delta
And
fx.
shouldn't them be gradient G?
Yes, here, right? Correct. So this is gradient G. Thanks for pointing this out. So this is correct. So this has to be gradient G. Okay, and so the same system, Ax equals B, okay, and x greater than 0. So that's the system which is feasible. Okay. So that would, what would that be? Can somebody tell me? Can someone translate to what this would be?
Grad of a summation UI grad G.
So grad fx star, right? What is it going to be? Grad fx star.
Summation UI into.
So grad fx star equal to something, right? Because b equals ax. So let
equal
me
to
say,
minus summation into, so summation of GI into mu I.
yeah, summation of gradient of gi.
Sorry, gradient.
Gradient of gi x star. So I'll just call this multiplier as lambda. Okay, so just to distinguish the two cases, the inequality and equality cases. Okay, so this would be gradient of fx star plus summation I lambda I gradient gi x star equals to 0, and also okay, and also you have lambda is are greater than or equal to 0. Okay, so lambda is are greater than or equal to 0. So this is the equivalent condition you would check. Okay, so these are all necessary conditions, but they're not sufficient. Okay, so let me just pause here. Are there any questions so far? Is this all clear? Harsimran, is it clear?
Yes, ma'am.
Yes, okay. Devansh,
I'm having some difficulty to understand. I'll have to review again.
say it again.
I'm having difficulty understanding. I'll have to review again all the previous concepts that I can understand this.
Okay. Okay, so let me know if there's some part which I, if you think explaining further will help you. Okay.
Yes, please.
Yeah, so it's just to understand it in simple ways, it's just an application of Fatka's lemma, and you just see in which direction the constraints should increase or whether it should decrease, and also the function value. Okay, it's just putting all of this together. Okay. Maybe somebody else. So Siddharth Solanki, is this clear or?
My case is also same as Devansh's. Like I got lost in algebra. I will have to like revise previous concepts and see this again.
Okay, so is this intuition clear, like in terms of, this part that I showed you, in terms of what's going on at these points?
Yes, ma'am. The intuition is clear. At least that is clear.
That is clear? Okay. So if that is clear, then it's just a matter of, writing it formally in terms of the Taylor series approximations. And, then you just apply Fatka's lemma. So you have to apply the right version of Fatka's lemma. So yeah, that's all there is in this proof. Okay. So now one thing to notice, some books will take these constraints as, greater than or equal to. So like G1x greater than or equal to 0, like that, they will treat it in that way. So in that case, there'll be a small difference here. So instead of delta fx star plus, it's going to become delta fx star minus summation lambda I. Okay, so that's not very hard to show. Like if you just follow these steps, I mean, it's just a matter of substituting the right constraints. Okay, so I would say to understand one form correctly, and then if you have some other forms, you can transform it to this one and then apply these whatever you've learned here. Otherwise, if you try to understand too many things, it gets confusing. Okay. But at some point, once you have understood these concepts, then you should try to also apply it to the case where if you have G1x greater than or equal to 0, what happens? Okay, you could apply this, I mean, you could do these steps algebraically, or you could also see it in terms of these ideas, in terms of what happens geometrically. Okay, so now so we looked at the case where you have equality constraints. We looked at the case where you have inequality constraints separately. So can we look at the case where we have both? Okay, so if we have both equalities and inequalities, so something like the most general form is that, right? You're going to have, gix is less than or equal to 0 for all I, and you have a jx is equal to 0 for all j. Okay, so j is from 1 to L, and this is from 1 to M. Okay, so in this case, what you can do is you can just convert all of this into inequality form. So this is equivalent to saying hjx is less than or equal to 0, and minus hjx is also less than or equal to 0. Okay. So again, this is for all j is 1 to L. So now if you write down, now you can just apply the same constraint. So it was that gradient of fx star plus summation lambda I gradient of gi equals 0. So let's just see that. So I'll just call these multipliers lambdas for each of these. And for these multipliers, I'll just call it, let's say, mu and maybe some tau. Okay, so what's going to happen is I'll just have delta fx plus summation I lambda I delta I gx, okay, plus summation I mu I gradient of mu j gradient of hjx minus again tau j gradient of hjx. This is going to be equal to 0. Okay, and lambdas are all greater than 0, mu's are greater than 0, and tau's are greater than 0. Okay, so if x is optimum, then this is true. Okay, so then this just means that you can simplify this a bit further. So you will get delta fx plus summation lambda I delta gix. Now, in terms of the j's, if you take the delta hjx, then you can get mu j minus tau j. So this is, if you just write mu j minus tau j, and you can just write it in terms of these. So these variables, if you take mu j minus tau j and write it as, some other variable, say rho j. Okay, so this is equal to 0, and lambda is are greater than or equal to 0. And rho j, you remember that was mu j minus tau j, and so it is unconstrained. Okay, so rho doesn't have, rho is unconstrained. So unrestricted, I should say, it's unrestricted. Okay, so this will be the equivalent conditions if you have both. So you see that, it's like you treat, it's as if you can treat these inequalities and the equalities separately itself. So if you looked at the inequalities alone, you would have these lambda I multipliers, and those are greater than or equal to 0. And if you treated these edges separately as equalities, you will have these delta j times rho j, where rho j was unrestricted. So you can bring all of it together. Okay. So that's how you will get these conditions. Now these lambdas and rhos, okay, so these are called the Lagrange multipliers. Okay, so in order to unify all of this in one way, so one thing to remember here is again this summation for these gradient gi and gradient aj, it's only for the active constraints. Okay, so now for equalities, all these are going to be anyway active. Now here this should only be for the active constraints. So I'll just write this as A. So only at the constraints which are active. So out of the G's, you look at only the constraints which are active at the X, and only for those you will have the summation. Okay, so there's something to unify all of this. We have what is called a Lagrangian function. So let me just go to that. So Lagrangian function is a function of any x, that is your decision variables in your original optimization problem. So the original problem is this. Okay, so this Lagrangian function also depends on the way in which you write the optimization problem. So I'm going to write the Lagrangian for this form. So gix is less than 0 and hjx is equal to 0. Okay, so this is my optimization problem. And so for this form, the Lagrangian is written this way. So this function is called a Lagrangian. It's a multiplier, it's a function of these x, and there is a multiplier for each of these constraints. So lambdas are the multipliers for gi's, and mu's are the multipliers for these edges. Okay, so the function is written this way. So f of x plus summation lambda gix plus summation mu j hjx, and in particular the summation for the gi's is only for the constraints which are active at x. So what this means is a of x is the set of all constraints for which gi of x is 0. Okay, so only for all these constraints you will include this. So instead of writing it in this way, what you will do is you will just add something like this: lambda I gix is 0. Okay, so that if gix is inactive, so if gix is strictly less than 0, you have lambda is 0, and otherwise it's okay. You will include a lambda here. Okay, so all these the conditions, these optimality conditions that we saw earlier, you can just write it in a condensed form, that the gradient of this Lagrangian with respect to x is 0. So that will give you gradient fx plus lambda I times gradient gi, so summation of this, plus mu j times gradient of hj. Okay, so that's just going to capture that constraint. And this lambda I gix equals 0, that captures this thing that you want to only account for the active constraints when you write the Lagrangian. So that's where you have this. And lambda i's are greater than or equal to 0, that we have seen. And also x is a feasible point, right? So it is optimum, it has to be feasible as well. So that's why you have gix less than or equal to 0 and hjx equal to 0. Okay, so a point x lambda mu which satisfies all these constraints is referred to as a KKT point. Okay, so KKT stands for Karush Kantakar. So we'll just see in a few, we'll see a little later, like these are the conditions for optimality. Okay, so an x lambda mu satisfying all these, that is called the KKT point. So if you're asked to find the KKT point, you just try to satisfy these set of equations, and inequalities. Okay, so one thing is, the KKT points have to do with the optimum, with the optimality conditions. But before we get there, there's one technicality that needs to be resolved, which is that of a regular point. Okay, so maybe I will come to this in the next class. So just to give a summary, it's just that, whenever you have X optimum, you want these, it means that these conditions have to be satisfied. Okay, so it's a necessary condition, but it's necessary only when that optimum point X is what is called a regular point. Okay, so there's one more technicality here. So I'm not going to prove this. We're just going to state it and use it, in the problems we solve. Okay, because I think a proof of this will get into a lot of other details, which I think it will just take the focus away from this course and the purpose of this course. Okay, so maybe I will do this in tomorrow's class. Okay, so yeah, so tomorrow we meet at 9. It's a Tuesday schedule, but we'll start at 9. Okay, so I think, yeah, we'll stop here and we'll hang back for any questions. So if not, if you don't have questions, so thanks for being here.